Good morning. Today's topic is Introduction of Electromagnetic Fields. Firstly, we divide these electromagnetic fields into two topics: electric field and magnetic field. This is electric field. Another one is magnetic field. So this electric field is due to static charge, and this magnetic field is due to moving charge. Okay. Now we are going to define this electric field and magnetic field. For that, first electric field. So consider a point charge here. This is a static charge. Whenever we have a static charge, it produces electric flux around it. So from electric charge, the electric flux lines are diverging. Okay. This effective area, which consists of electric flux lines, is an energy area of this static charge. Okay. This energy area is called electric field. Okay. So now we are going to define this electric field as an energy area around the static charge. Next one is magnetic field. So here electric field is due to static charge. In this magnetic field, it is due to moving charge. So when we have a moving charge here, this moving charge produces circular magnetic flux lines. So this effective area which consists of magnetic flux lines are an energy area of this moving charge. So we can define this as an energy area around this moving charge is called magnetic field. Okay. So energy area around this moving charge is called magnetic fields. Now we defined this electric field and magnetic field. Combination of both electric and magnetic fields are called electromagnetic fields. Okay. So electromagnetic fields means it is a combination of electric field and magnetic field. So in our syllabus, we are going to discuss the electric field in first 3 units and finally magnetic field in last 2 units. So now, for understanding EMF, we must be well versed in the following topics. First one is EMF symbols and its units. And then vector calculus. Last one is coordinate systems. So first we are going to discuss about this EMF symbols and its units. EMF symbols in the left side and its units are in the right side. So first one is electric field intensity. That is represented as capital E vector. Its unit is volt per meter. Is voltage per unit length is called electric field intensity. Okay. Likewise, magnetic field intensity is defined as magnetic field intensity H vector is defined as current per unit length. Current per unit length, it is represented as capital H vector. So third one is electric flux density. So electric flux density is represented as capital D vector. Its unit is coulomb per meter square. That is charge per unit area is called electric flux density. Okay. Fourth one is magnetic flux density. So magnetic flux density, it is represented as capital D vector. Its unit is Weber per meter square. So magnetic flux per unit area is called magnetic flux density. Okay. Next one is electrical permittivity. So fifth one is electrical permittivity. That is represented as epsilon. Its unit is farad per meter. Its unit is farad per meter. That is, so consider this as a medium. How much amount of electric field it can permit? That is called electrical permittivity. Okay. So how much amount of electric field is permitted by this medium is called electrical permittivity. So sir, last one is magnetic permeability. Magnetic permeability. It is represented as mu. Its unit is Henry per meter. By understanding all these symbols and units, we are going to get the most important relationship in EMF. So, relationship between field intensity and flux density. For this relationship, we need some basic formulas. Okay. For capacitance, we have Q by V, that is charge per voltage. From this we can get a Q is equal to CV. Okay. Here its unit is coulomb and its unit is farad. Voltage unit is volt. Then we are going to divide meter square on both sides. So we can get coulomb per meter square is equal to here farad per meter into volt per meter. Now check the units here. For coulomb per meter square, we have electric flux density. Okay. So coulomb per meter square, we have electric flux density d vector. For farad per meter, so farad per meter, we have electrical permittivity. So it is epsilon, and volt per meter we have electric field intensity. So it is E vector. So electric density B vector is equal to electric permittivity into electric field intensity. And then for magnetic field we have this formula, inductance equal to I by I is flux per current. Okay, magnetic flux per current. From this we can get phi is equal to LA. Okay, its unit is Weber. Likewise, this has a unit of Henry and a current it is ampere. Then we are going to divide meter square on both sides. So Weber per meter square, that is equal to Henry per meter into ampere per meter. Now we check the Weber per meter square here. So Weber per meter square is for magnetic flux density. That is B vector is equal to Henry per meter. It is the unit of magnetic permeability. That is mu, and ampere per meter for magnetic field intensity. That is H vector. So it is B vector is equal to mu into H vector. Magnetic flux density is equal to permeability into magnetic field intensity. Okay, these are the two most important relationships between flux density and field intensities. Our next topic is vector calculus. So the second topic is vector calculus. Here we are going to introduce one important operator in vector. Okay, that is del operator. It is represented as this one. So formula for this vector operator is del is equal to rho by rho x of ax vector plus rho by rho y of ay vector plus rho by rho z of az vector. So that is equal to rho by rho x of ax vector, rho by rho y of ay vector plus rho by rho z of az vector. It depends on the x, y, z axis, so it is a spatial related. So it is spatial, and also it is rho by rho x, rho by rho y, rho by rho z. This is for derivative, so spatial derivative, and also it has unit vectors ax vector, ay vector, and az vector. So spatial derivative vector operator. So this del is called spatial derivative vector operator. Now we are going to use this vector operator for scalar and vector quantities. Now whenever we need the maximum distance or maximum value in a particular direction, we need this gradient. This gradient means del dot scalar value. So del dot scalar value gives the gradient operator. Okay, that is del f is equal to gradient. It is a here f is a scalar quantity. Okay, del is a vector quantity, f is a scalar quantity. So resultant of this gradient is always vector. Okay. Next one is divergence. Whenever we have an electric charge or static charge, it produces the electric flux line in a diverging manner. Okay, at the time we should use this divergence, that is del dot vector, del dot A vector. Okay, this is called divergence. Del dot, the dot product of del and vector quantity is a divergence. Resultant of this divergence is always a scalar quantity. So resultant of this divergence is always a scalar quantity. Resultant of the gradient is always a vector quantity. Likewise we have curl operation. That curl operation is whenever we have a magnetic field, that is a circular motion or circular field, we need this curl operation. Okay, so curl means del cross one vector quantity, so that is del cross A vector. Okay, this is called curl. Whenever circular field is there, we must use this curl operation. Okay, here resultant of this curl is always a vector. So curl resultant is vector, gradient resultant is also a vector, and also divergence resultant is a scalar. These are the three important results which are asked in the gate examination. Okay, so the next topic is coordinate systems. First we define a coordinate system. Consider this is an object or dot. How can we represent this dot or point or object in a three-dimensional space is called coordinate systems. Okay, so it is a way of representing point or object in a 3D space is called coordinate system. Okay, it is a way of representing. I am going to represent this object in this three-dimensional space. Okay, that is called coordinate systems. So based on the shape of the coordinate systems, we have multiple coordinate types, coordinate system types, but in our curriculum we have three types of coordinate systems. First one is types of coordinate systems. The first one is rectangular or Cartesian coordinate system. The second one is cylindrical coordinate system. The third one is spherical coordinate system. These types are based on the shape of this three-dimensional space. If a three-dimensional space is rectangular in shape, that is called rectangular or Cartesian coordinate system. If it is in cylindrical shape, that is called cylindrical coordinate system. If it is in sphere, that is called spherical coordinate system. Okay. Here we are going to compare all these coordinate systems here. So rectangular, cylindrical, spherical. So first one is, all these coordinate system consist of 3 axes. So those are, in rectangular coordinate system we have x, y, z axis. Here in cylindrical coordinate system we have rho, phi, z axis. Likewise in spherical coordinate system we have r, theta, phi. Okay. So second, these are the axes. So x, y, z are axes. We have the range of all these axes are minus infinity to plus infinity. Because in our graph sheet we have positive and negative x axis and also positive and negative y axis. That is the 2-dimensional sheet. Here we have coordinate system is a 3-dimensional space. So it is having x, y, z. All are having positive and negative limits. Okay. Here all these coordinates are having minus infinity to plus infinity range. Okay. And then cylindrical coordinate system has rho is the radial distance. So it is starting from origin. So rho has 0 to infinity range and phi has 0 to 2 pi range. 0 to 2 pi angle. This one is angle here, and z is always z is same as this rectangular coordinate system. So it is minus infinity to plus infinity. It is just a line. Finally, we have spherical coordinate system. Here we have 2 angles and 1 radial distance. First one is, so r has the limit of 0 to infinity, because it is starting from origin, then it is going to infinity, and then theta is an angle. It is a lookup angle. Okay, so lookup angle must be 0 to 181. Okay, so it is 0 to pi. Finally, this phi has 0 to 2 pi. It is a orientation angle or turnaround angle. Okay, so phi is same as this cylindrical coordinate system.